Okay, your position looks good, Joe. Let's go Delta Psi on.
Haven't got the 1 minute warning yet. One minute. Delta Psi. Push to test. Rock light showing. Prime. Igniter ready light. Pre-cool on. Igniter idle. 20 seconds to launch. Everything checks here.
Your position is good, Joe.
Pump idle. Good pump. Good igniter. Ready to launch now. Good light. Okay.
This is the X-15 research aircraft, designed to investigate the problems of manned flight in a near-space environment. Altitudes up to 50 miles, speeds up to Mach 6. High-speed aerodynamics, aerodynamic heating, structural design, aircraft stability, and control in space and re-entry. This was the kind of information it was to provide, and provided it did. Here's the story. Before the X-15, the question had been, what is to be man's role in space travel? Can he pilot an aircraft out of the Earth's atmosphere, fly it in space, then re-enter the atmosphere and bring it back to a safe landing on Earth? There were many unknowns to be discovered, many problems to be overcome before the answer would be known. That today's test flight is almost routine is a tribute to the comprehensive program that has moved step by step to prove that man can pilot an aircraft into space and return.
Give us a 20,000-foot check, Joe.
Coming up on 20,000 now.
Okay, I know you've done it, but check your flaps and circuit breakers.
Roger. Done.
Ready to go pressurize?
Pressurize.
You're in good shape.
Flaps. And flaps are coming down. Gear. Can't seem to get her on the ground. Real nice. Well, sir, now we're done with the second cross country. Yeah, boy.
Real good flight, Joe. This is your happy controller going off the air.
There have been many men who have helped make the X-15 project a success. One of them is aircraft research engineer Hartley Soule, who was originally in charge of designing and building the X-15 aircraft.
Of course, I'm retired now, and the X-15, she's not the queen of the hangar anymore, although she's still hard at work. But I remember years ago, you know, it was long before Sputnik that we decided to build the X-15. This airplane, the first hypersonic aircraft, was going to be our first manned space probe. This was a logical step in the research aircraft program that had begun even before the end of World War II.
From the beginning, the research aircraft program was a cooperative affair. The National Advisory Committee for Aeronautics, predecessor to NASA, the aircraft industry, the Air Force, the Navy, working together. Their first effort was directed at breaking the sound barrier. And the aircraft that would do it was the X-1, designed to acquire flight data at the speed of sound. On October 14th, 1947, with Air Force Captain Charles E. Yeager at the controls, the X-1 made the world's first supersonic flight. Other research aircraft soon followed the X-1. The Douglas D-558 Phase 1, to investigate flight with a straight wing at high subsonic speeds. The Northrop X-4, designed to fly without a tail. The Douglas D-558, Phase 2, to study flight characteristics of swept-wing aircraft at transonic and supersonic speeds. The Bell X-5, designed with variable sweep. And the Douglas X-3, to investigate thin, straight wings at speeds beyond Mach 1. The Bell X-1A, with its increased performance, first of a series of follow-on aircraft to the original X-1. The X-2, another Bell airplane designed to explore aircraft behavior at altitudes above 100,000 feet and Mach 3 speeds. The X-1E and X-1B, both later follow-ons to the X-1. Step by step, these different aircraft helped nibble away at the unknown, until by 1956, the frontiers of manned flight had been advanced from speeds of 500 miles an hour to Mach 3, and from altitudes of only 40,000 to more than 100,000 feet.
Speed, altitude, sure we kept going higher and faster than we'd ever been before. Only because that's where new information, where the unknown has always been found in flight, above and beyond the limits you've already reached.
As early as 1952, the X-15 aircraft was being conceived by the people at NACA. At the Langley Center in Virginia, they began investigating the unknowns associated with flight to the thinnest edges of the Earth's atmosphere. One unknown concerned aerodynamic heating. The X-15 would be the first aircraft to push from supersonic to hypersonic speeds, where the flow of air would heat the leading edges of the plane to 1,300 degrees Fahrenheit. Experiment after experiment was run to see if this extreme temperature would weaken or melt basic materials. The data resulting from tests run well beyond temperatures expected for the X-15 proved that there were materials that would withstand this kind of heat. Another problem, after rocket engines shut down, the X-15 would be thrust into a ballistic arc in air so thin that normal aerodynamic control would be impossible. How then could the pilot control the aircraft? The answer? Reaction controls that would allow him to correct roll movement and position the aircraft properly for re-entry through the atmosphere. But the designers knew the problems of control would never be fully solved until an X-15 aircraft was actually built.
We knew the X-15 would look something like this. We knew that it would be a manned aircraft that would fly more than 4,000 miles an hour and as high as 250,000 feet. We knew that like the X-1, the X-15 would be air-launched and propelled in its flight by a rocket motor, the most powerful engine ever installed in an airplane. Of course, we didn't know what kind of a rocket motor that would prove to be.
There'd never been anything like it. Designed for a manned system, the 50,000 pounds of thrust in its single chamber had to be controllable at the pilot's discretion. He had to be able to throttle this engine in flight.
This is Harry Cook, program manager for the X-15 rocket engine.
The LR-99 rocket engine was designed and built for the X-15 by the Reaction Motors Division of the Thiokol Chemical Corporation. We had had some experience in this field. Reaction Motors had built power plants for all of the X-1s and for the D-558 Phase 2 aircraft. But those rocket engines we had made for earlier research planes were primitive forerunners of the engine we built for the X-15.
57,000 pounds of thrust with a throttle attached. No engine like this had ever existed before, but Thiokol built one for the X-15. Now, what kind of airframe could be designed to carry such an engine?
The X-15 was designed and built to take the stresses encountered at hypersonic speeds, to go to extreme high altitude and to beat the heat, survive the extreme high temperatures that build up on the wing, fuselage, and tail during the re-entry to the Earth's atmosphere. The engineering research contribution we made at North American Aviation to the X-15 project was to take NASA's proposal to build this aircraft and to find out how they could be met.
Harrison Storms. He was in charge of the X-15 program at North American Aviation.
For example, they proposed to use a new nickel alloy metal for the protective sheath or skin on all three of the airframes of the X-15. We had to find out how it could be used.
Inconel X was the name of the new nickel alloy. It was developed to withstand the searing temperatures at hypersonic speeds, temperatures of 1,200 degrees Fahrenheit or more. But to use Inconel X, it had to be cross-welded, and no one had been able to do it before. A major milestone was passed when North American discovered how it could be done. North American also originated the idea of fairings along each side of the X-15 fuselage to house control cables and hydraulic lines. This left the entire fuselage volume for power plant plumbing, as well as fuel and propellant tanks. Another invaluable North American contribution was the X-15 flight simulator, permitting pilots and ground controllers to plan and practice flights without ever leaving the ground. From an exact replica of the X-15 cockpit, the pilot could actuate hydraulic and control systems identical to those on the aircraft itself. All this was tied into an analog computer that could program actual X-15 missions and simulate every conceivable in-flight problem the pilot might expect to face. Practice in the flight simulator was just one phase of pre-flight preparation. Another took place in the centrifuge at the Navy's Air Development Test Center at Johnsville, Pennsylvania. There, pilots learned how to take the heavy G forces they would meet when they flew the X-15 up into space and back down again. Hours of training here, added to hours in the simulator, extended the pre-flight pilot training period into weeks and even months. Then came the dramatic moment. The X-15 and its B-52 launch aircraft were ready. North American test pilot Scott Crossfield was ready. Step by step, the X-15 research project had moved to this important event. Now, the first of 3 X-15s was about to begin a series of test flights. The schedule called for an orderly progression of tests. In the first flights, the X-15 would remain attached to the B-52. Then a glide flight would be tried. Only then would powered flight be attempted. This careful program of flight tests, flown by pilot Scott Crossfield, proved the X-15 would do just what its designers hoped she would.
From March 10th, 1959 until late in 1960, when we delivered the 3rd aircraft to the Air Force, I made 14 captive flights, 1 glide flight, and 10 powered flights. It was all pretty much routine. We, North American that is, went up there to check out the aircraft, to check out the systems, to see how she handled and whether or not she'd meet the specs before we turned her over to the Air Force. But you'll have to go up to NASA's Flight Research Center at Edwards to find out how the actual test programs worked.
Edwards Air Force Base in the Mojave Desert in California. This is where the X-15 story comes together. For here is where test flights of all high-speed research aircraft since the X-1 have taken place. Like all the programs conducted here, the X-15 Flight Research Project had a simple basis. A series of progressive steps to higher speeds and to higher altitudes. But each step, each flight itself, had a more immediate purpose than simply to gain more speed or altitude. And each flight was carefully planned to make the most effective use of this aircraft as a research vehicle or tool. Paul Bickle, director of NASA's Flight Research Center.
Each flight provided new information or confirmed one tunnel or theoretical data on the characteristics of an airplane performing in a very advanced flight regime. Each flight grew out of one that had already taken place and led to another still to come. But of course, the X-15 flight program really began in the simulator months before the first airplane was delivered to us.
Joe Walker, Chief NASA Edwards research pilot, physicist, and pilot of a long list of research aircraft.
Practice or planning in a simulator is the beginning of every flight that's ever been made in the X-15. All pilots assigned to the project first become familiar with the handling characteristics and timing of the X-15 on any given mission in the flight simulator. It's been good insurance for all of us.
One of the X-15 pilots who has spent many hours in the flight simulator is NASA's Milton Thompson. Here, Thompson flies a practice mission under normal procedure, with pilot engineer John McKay working as his flight planner. In a nearby room where the analog computer is housed, the activity in the cockpit can be monitored on closed-circuit TV. The pilot's control movements and the airplane's simulated response are checked on a plotter by the flight planner, who will monitor the actual flight from the NASA Edwards Control Center on the ground. The pilot's inputs may also be monitored and recorded by other instruments. Variations from the planned mission are then simulated, so the pilot will learn to recognize their effects on the aircraft. For example, he may get a problem involving changes in stability. These changes are fed by the computer to his cockpit instruments. The pilot reads the changes and makes control inputs to bring the aircraft back to normal. His response is monitored and evaluated. The pilot also goes through what is called trouble school, where failure of one or more of the X-15's major systems is simulated. Again, his reaction is monitored. Each pilot gets further practice by making a number of flights in a modified F-104 aircraft. He flies over his upcoming X-15 flight course to establish geographic checkpoints and key altitudes in the landing pattern. All flights are made over the high range, a network of ground tracking stations stretching from Wendover, Utah, 485 miles south to Edwards in California. The range consists of a master station at Edwards and radar stations at Ely, Nevada, and at Beatty. The flight corridor is 50 miles wide, and it contains a number of dry lake beds where emergency landings can be made. Two kinds of powered flights are made over the high range. One, a ballistic type, high-altitude run up to and even above 250,000 feet. And two, a high-speed run made at a lower altitude, usually 60 to 70,000 feet. During his practice flights in the F-104, the pilot must also familiarize himself with the timing and positioning for an X-15 landing at both primary and alternate landing sites. And he makes practice landings, using predetermined settings that can simulate the low lift drag ratio of the X-15. Nothing is left to chance, in the air or on the ground.
These precautions paid off during the following flight, when the pilot realized he could only get 30% power, and that consequently he would have to make an emergency landing at Mud Lake.
Ready to launch. 5, 4, 3, 2, 1.
That's a good light, that's a good light.
Hello, on thrust, give us the chamber reading.
Got 12 degrees.
Okay.
Chamber pressure.
Tank pressure's at 50.
Push your throttle up and give us chamber pressure.
We don't have chamber pressure, about 200.
Roger, you got the full throttle?
Up there.
You're running at 30%.
30%? How are we doing, Bob?
Roger, you're going by Mud Lake. It looks like a landing at Mud Lake.
Roger. Looks from the smoke down there like there's a very tiny bit of wind from perhaps south and a little bit east. There's nothing.
Wrecked though it seemed to be, both the aircraft and the pilot survived to continue with the program. This was one of only 3 major accidents, all non-fatal, that have occurred in more than 120 flights with the X-15, a remarkable record of reliability. In February 1964, the plane that crashed on Mud Lake only a few months before came rolling out of the North American plant with a new designation, the X-15A2. This modified version was rebuilt for flight to Mach 8, 8 times the speed of sound, where the airflow temperature rises to 2,400 degrees Fahrenheit. The new X-15 had a new heat-resistant protective coating, a new inertial guidance system, a longer fuselage, external tanks to carry more fuel for longer flights, and lengthened landing gear. All the while this new X-15 was being built, tests were continuing with the other 2 aircraft, and they continue today. For every flight, the procedure is essentially the same. Every phase carefully planned, every second of actual flight time mapped out in advance. That way, every man involved knows exactly what his job will be from the beginning to the end of the flight. Hours of preparation, weeks of planning, months of study, whole years of research. All this goes with the X-15 each time she leaves the hangar for another flight. For after all, no matter how many flights have been made before, each new test will probe a little deeper into the unknown. She is a research tool, this sleek black aircraft, carrying a host of instruments, gauges, and recorders to explore the unknown. And every second of her time in flight must be carefully charted. That's why at the Ely High Range Station, at Beatty, at Edwards, sensitive antenna watch and listen to each flight. That's why the pilot's heartbeat never really leaves the ground. And that's why in each control room on the ground, the plotting board is carefully watched for any unplanned deviation, for any unlooked-for change in the pilot's reactions or in the behavior of the aircraft. Position and velocity computers, telemetry receivers and monitors, data receiving and recording equipment, communications receivers and transmitters, they all go into action at the beginning of every flight. In NASA 1, the project men stand by, alert for any possible trouble in the flight, while flight surgeons prepare to watch the pilot's physiological response, his pulse, his body temperature, heart action, respiration rate. All of this will be telemetered to the ground. Then, as always, when time for takeoff draws near, attention focuses on the man chosen to fly the mission. Because of this, the X-15 pilot becomes, in effect, the symbol for the entire research team. The one man who represents all the others who have worked so long and so hard to make the project a success. And it is a proud record of accomplishment they've achieved. They have designed and built an aircraft that could be piloted into space and flown back safely to a controlled landing on Earth. They have accumulated important data on aerodynamic heating at hypersonic speeds. They've learned about stability and control of aircraft during flight in near space and re-entry to the Earth's atmosphere. And perhaps most important of all, they have dramatized the potential of piloted high-performance aircraft in a space environment at a time when much of the world's gaze was turned toward orbital flight. The X-15 research project has long since achieved its original goals. The aircraft has been flown successfully more than 120 times, and although setting new records wasn't its purpose, it has set a few along the way. Altitude, 67 miles. Speed, Mach 6, 4,104 miles an hour, the highest and fastest a winged aircraft has ever flown. Today, the X-15 moves on to further accomplishment. But now the Thoroughbred has become a workhorse, carrying a heavy payload of instruments, undertaking studies of the near-space environment possible before only with unmanned satellite and rocket-borne probes. There are many people who should share the credit for the continuing success of the X-15 research project. But perhaps they will understand if we seem to focus on those who have actually flown the many research aircraft since the X-1. By saluting these courageous men, we also pay homage to all the others who have helped us move step by step, deeper and deeper, into the unknown outskirts of space.
Real good flight, Joe. This is your happy controller going off the air.
There have been many men who have helped make the X-15 project a success. One of them is aircraft research engineer Hartley Soule, who was originally in charge of designing and building the X-15 aircraft.
Of course, I'm retired now, and the X-15, she's not the queen of the hangar anymore, although she's still hard at work. But I remember years ago, you know, it was long before Sputnik that we decided to build the X-15. This airplane, the first hypersonic aircraft, was going to be our first manned space probe. This was a logical step in the research aircraft program.
Story. Before the X-15, the question had been, what is to be man's role in space travel? Can he pilot an aircraft out of the Earth's atmosphere, fly it in space, then re-enter the atmosphere and bring it back to a safe landing on Earth? There were many unknowns to be discovered, many problems to be overcome before the answer would be known. That today's test flight is almost routine is a tribute to the comprehensive program that has moved step by step to prove that man can pilot an aircraft into space and return.
Give us a 20,000-foot check, Joe.
Coming up on 20,000 now.
Okay, I know you've done it, but check your flaps and circuit breakers.
Everything checks here.
Your position is good, Joe.
Pump idle. Good pump. Good igniter. Ready to launch now. Good light. Okay.
This is the X-15 research aircraft, designed to investigate the problems of manned flight in a near-space environment. Altitudes up to 50 miles, speeds up to Mach 6. High-speed aerodynamics, aerodynamic heating, structural design, aircraft stability, and control in space and re-entry. This was the kind of information it was to provide, and provided it did. Here's the
Okay, your position looks good, Joe. Let's go Delta Psi on.
Haven't gotten to 1 minute warning yet. One minute. Delta Psi. Push to test. Rock sign showing. Prime. Igniter ready light. Pre-cool on. Igniter idle. 20 seconds to launch.
Breakers.
Roger. Done.
Ready to go pressurize? You're in good shape.
Flaps. And flaps are coming